Right, I've set up a force diagram on this question so that the focus is on object A, object B, right? And we can resolve then on object A, object B. We can focus in on those two particular objects, right? So if we look at the fact now that there's friction on this table because it's a rough table, they've given us the coefficient of friction value to be 0.4. So now we can resolve. So if we resolve at A, okay, in the direction of motion, okay, so we're using Newton's second law, okay, obviously throughout this process, okay. In this case now, in the direction of motion, we have the leading force, the tension in the string, isn't it, which is pulling, this tension is pulling this object. Of course, there's a resistance then of the friction. So the overall resultant force is T take away Fr, okay, and that will equal to the mass times acceleration. So the mass of object A is 5, and times the acceleration then, which is A. Alright, so I'll write it down here as well. Of course, my focus is on object A. If we resolve vertically, now of course there's no acceleration vertically because the object is staying on the plane. So we could literally say, look, forces up is equal to forces down, so R is equal to 5G. Okay. The object is in motion, so that means friction is at its max. So we can say, look, friction is equal to mu R. Okay. But what's great about that is then, because I know mu in this case to be 0.4, okay, I can actually work out what friction is. So 0.4 for mu times then the reaction, which I get from here, which is 5G. Okay, so 5 times 9.8. On my calculator, I get the answer out to be 19.6 newtons. Okay, so that's my frictional value when it's in motion. Okay, and that's the max friction essentially for the value of mu equals 0.4. Okay, now if you think about that then, because we know friction is 19.6, I can then put it in there, can't I? So I could say therefore T take away 19.6 equals 5A, and I've got kind of a nice equation then with two unknowns. So I'll call this maybe equation 1. So then if we look at B, at object B, we can resolve then in the direction of motion, right? Which of course is vertically. Okay, nothing's happening horizontally, this is just going down, isn't it? So we've got the weight taking the object B down. Of course there's a resistance, of course the tension in that string is holding it up, it's stopping object B from falling freely under gravity. Okay, so that tension in the string now, which is attached to particle A, we take away, so that's my resultant force, and that will equal then to mass times acceleration. So the mass of course of B is 3 times acceleration. So I've got two nice equations, and these are nice straightforward to work these out, because all you need to do then when you solve them is you add them. Alright, so if we add them, the t's will cancel, won't they, if you think about it. So if I do 1 plus 2, I'll have t here, add the minus t, they will go. I've got minus 19.6, add the 3g, of course 3g will be 3 times 9.8, and then add these, so that becomes 8a. So a bit of calculated work here. Minus 19.6, add 3 times 9.8, and we get 9.8 equals a, or equals 8a rather. And then to get a then, I need to do 9.8 divided by 8, and I get 1.225 meters per second squared. Okay, so I've got my acceleration, and you need to remember then the acceleration is the same throughout the whole system, right? Throughout the whole system here, because that string is taut. Okay, it's over a smooth pulley, so the acceleration is the same throughout. So we've got the acceleration, we also need the tension in the string. So to get the tension, I just need to sub it in now to one of these. So sub it into my 1, right? So we can say, look, sub into 1. So we have T take away 19.6 equals 5 times A, which is 1.225. And then to get t then, I just need to work that out on my calculator. So times 1.2225 by 5, and then add on 19.6, so we get 25.725 newtons. Okay, there's your tension. Now, part B, it says, given instead the bodies remain at rest, find the least value of the coefficient of friction. So we've got exactly the same setup as we've got here, but it's not moving, okay? So it's at rest, it's saying. So obviously, if that's the case, the value of mu has got to be different to the value of mu that we had here. Because if it was 0.4, the system would move, okay? As we've just worked out, we've got a tension established, but we've got an acceleration, yeah? It's moving when mu is 0.4. So if the case if it's not moving, right? So basically it's stationary, then that friction here is strong enough to keep everything in place. But if it's not moving, we need to appreciate then these equations that we've got here will be, especially let's focus on these ones, the equations we've got here will be different, okay? But also our friction will be different as well. So perhaps I'll ignore this one, because remember we worked out our friction to be 19.6, but that was when we had our mu to be 0.4, okay? So mu now is going to be different. So let's just look at this one here then. Okay, so if there's no motion, right, then at A, no motion, that means then if there's no acceleration, so we'll have T minus Fr will be mass times 0. So it'll be 0. So in other words, T will equal Fr. Okay, tension will equal the friction. And the same would be the case at B as well. At B, okay, forces up will equal forces down. T will equal 3G. Okay, T will equal 3G there. And what you notice then is, if T is equal to 3G, that means friction, which is equal to T, will also be 3G. Okay, that's what friction will equal, 3G. So frictional force there will be the same as the tension, which is the same as the weight here. So friction will be 3G. Now friction is 3G. Okay, remember, friction might not be at its max because it's stationary. Okay, since it's not moving, friction might not be at its max. In other words, friction is going to be less than or equal to mu r. It might be equal to mu r. It might be at its max and just holding it in place. It's on the point of moving, but it's still not moving. But we've got to assume it could be less as well. So if we sub that in, 3G here for friction, which we worked out, when it's not moving, it's equal to the weight of object B. Mu, and R, of course, we established earlier on, was 5G, wasn't it? There was R there. So all you've got to do, take that 5G over. The G's will cancel. You can see then mu, if we read that backwards, it's going to be greater than or equal to 3/5. In other words, the least mu is going to be 3/5. Okay, or 0.6.